everyone. My name is Farzana Zorabi, and I'm from Mississippi State University. We are group five of ExoEarth Finder project, and we are gonna talk about four different spectra that they gave us to find out the composition and figure out what type of planet we are looking for.
My name is Rachel Johnson. I'm a first year PhD student at the University of Denver.
I'm Giuseppe Frustagli. I'm from University of Milano Bicocca in Italy and from INAF Osservatorio Astronomico di Brera.
We made a few assumptions in our analysis. To begin with, we defined our habitable zone as being 0.75 to 1.7 AU. And then we also defined the minimum radius of these exoplanets capable of harboring life to be zero point 0.9 and it's supposed to be zero point 0.6 respectively. We used this equation here to approximate our planetary radii, and we assumed everything below 1.5 Earth radii to be a rocky planet and everything above to be gaseous. And additionally, all of our exoplanets are presumed to be orbiting sun-like stars. So this is our first spectra. We were able to identify some molecular oxygen and some water vapor in the atmosphere. However, we calculated our radius for this planet to be about 0.4 Earth radii, so very small, and to be orbiting its host star at about 2 AU. So while it does have O2 and H2O in its atmosphere, we've decided that it's probably not habitable because of its size and distance from its host star.
So the second spectra is this one, which if you look at the spectra, you can see O2, H2O, and methane, which is great, right? But if you look closer, you can see that, for example, here, we were looking for to see what type of spectra we are looking at, but it seems to be very huge absorption, and this is just like a gap between two huge absorptions. In the most spectra that I saw in the website that in the engine search was methane, but I'm really not sure that it's a black spectra or actually there is something there. If we look at the planet radius, it's about 4.8 Earth radii, and it's in the 2 AU from the star, which is just like our sun. So we had a list of questions that we had to answer. Is it a larger or smaller planet? Is 4.8 larger than Earth, but is it assumed to be a large planet? I'm not sure. It's a mini Neptune. What type of molecules do they have? We have water, we have hydroxide, methane, and oxygen. But because our range for being the largest habitable planet is 1.5 Earth radii, and we have 4.8, it's a low density gas-rich planet, so it cannot be habitable. And as I said before, it's a mini Neptune. Do we see any Wagner signature? Yes, we see water, we see oxygen, but we don't think that anything can happen because it's a gas planet. And follow observations, probably yes, because it's a big planet far from its host star, so it's a good option for observing, but not for looking for life.
For the first spectrum, we found an approximate radius of 0.2, so why so small? But we've also found many interesting molecules for habitability, water, dioxide, carbon dioxide, methane. But since it's such a small planet, a rocky planet, uh, so it is in the habitable zone, but for our calculation of minimum radii, it's too small for being a habitable planet candidate. So we put it in the medium priority for follow-up, even if it should not be habitable.
And the last spectra is this one, which seems pretty flat. It has a huge absorption that it doesn't give us almost nothing other than water. If you look at the planet radius, it's slightly bigger than Earth and definitely in the habitable zone because the habitable zone was between 0.75 to 1.7 IU. We have water, but again, it's the mini Neptune. It's more than 1.5 of Earth radii, and it's again a low density gas-rich planet, so it cannot be habitable. Uh, we have only water as the biosignature, but still it's the planet in habitable zone of the star, and it is slightly bigger than Earth, so probably it's a good option to observe it to just know more about the planet and maybe somehow with other type of imaging and I don't know if the technology goes a little bit further, we could get a better understanding of what type of spectra we are looking at because it seems that this planet has a hazy spectra or there should be maybe some clouds in it. That's why we don't get anything out of it. And this is a summary of all the planets that we have.
Based on your experience with this group project, did it change your answer to the poll question earlier of whether or not we will find a biosignature by 2040?
Well, no, I think still bisignatures are, we can find them, but yes, maybe life, it's not so easy to be found. So that's the same question answer I gave before. Yeah.
And there was one slide in Aki's slide that it was just the most advice that I got from the whole meeting was that it's easier to tell a planet is inhabited than it is habitable but lifeless. That was the yeah, that was the point of all the slides for me.
Just one question. On the first spectra, don't you think I'm here? Don't you think there is ozone in one of your spectra? I think the first one. First spectra, yeah. If I'm right, if I remember right. Yeah. The first, at the beginning in UV, this like this maybe would be ozone. It would be interesting. I don't know. I thought we had the same feature and we put it ozone, and so it could change. It could change how you follow up or not.
So that one didn't end up getting identified. So we were using the BPL molecular search engine to identify things, and it wasn't bringing anything up to that particular wavelength. So I was seeing in a lot of PowerPoints that that was what we were calling it, but I didn't want to, yeah. Yeah.
It's a learning experience.
think it was your third planet was 0.24 Earth radii, and yet it had an atmosphere. I was wondering if you had any comments on that.
Yeah, of course, it was an approximate calculation, so we are not sure about what is with this planet. That's what the numbers gave us. So.
Could you explain how you got such a precise calculation of what the radii were?
Yeah, well, we used the formula.
Okay. But I mean, there were things in that formula which I didn't tell you what they were.
Yeah.
So how did you figure them out?
We assumed an albedo of 1, and for the straight function, we assumed that it was 1, 2, because we didn't know what it was, and then we just put in the data.
Okay, I guess I do want to say one thing. Okay, that's why, assuming an albedo of 1, that's the maximal albedo you could have by theory, so that these are lower limits to your radii. So it's probably not a good idea to take them quite so literally.
It would help us to constrain the density of the planet, so it would help us to understand if we are going right, saying it is rocky, it is a gaseous planet, so having the mass would be of great help to constrain more our planets, and so what we see.
Okay. All right. So thank you. Let's thank the team again. All right. So can we have Exo Earthfinder Group 2 now? Okay, that's fine.
The computer sometimes freezes up, right?
Exo Earth 2 miles, right? Yeah. Okay. There we go.
I'm Miles Curry, and this is Samantha Gilbert, and this is Elsa Ducrow. The group researching oxygen molecules on planets to win Nobel, or Group 2. And these are our planets right here. So I will pass this on to Elsa.
Yeah, so I'll just go back to like the next group. Go back to this formula that we of course use to get an estimation of the planet's radius. So as the first group did, we kind of put an assumption on the albedo and the scattering function. So what we have is for the size of the planets, we have a range every time. And for the range, I use either an albedo of 1 for the lower limit, or an albedo of something like 0.3, something more terrestrial planets. So we have a kind of an upper limit and a lower limit, but we have a huge uncertainty on the mass, so on the radius, sorry. So we don't. It's just to distinguish between rocky and gaseous and that stuff. So if we just go to the first spectrum, what we identify here, we see clearly haze, I think, and then we have small figures, maybe of O2. We think about methane more than CO, and a lot of water. So yeah, this would, if we have to think about, like, it's more, it's at 1 AU, but it doesn't seem to be, or maybe it's habitable, but it's just not a lot of oxygen, so maybe it will be habitable. Well, you would see more oxygen. Maybe it's like kind of an old Earth or something like this. But so it's, what did we say about it? Oh, sorry. So we say, yeah, let's go for follow-up because it's going to be interesting. There is water in the atmosphere, it's in the habitable zone, so might be liquid water on the surface. Yeah, we say maybe like something like Earth, but maybe in all times. It has hazes, so it can hide some feeders. And yeah, but it's a bit uncertain about methane because we don't have enough precision on the point. So let's do follow-up. I will pass it to you.
So this is the second spectrum that we analyzed, and we approximated the radius at around 25,000 kilometers, so quite large. We imagine this is a giant planet, probably located outside the habitable zone of the star since it's at 5.2 AU. And then from the spectrum, we think that there's sort of a haze over here, a lot of water features again, potentially some methane features. And then towards the end, we decided it was too thermally noisy to decide. So personally, we're not going to flag this one for follow-up observation. No offense to gas giant people. Mostly because it's a giant planet, probably not in the habitable zone.
Okay, so for this next planet, we determined the radius was around 2,000 to 3,000 kilometers, and that it is a terrestrial planet on the inner edge of the habitable zone. So we found evidence of a little bit of haze right here, and some O2 features along with OH and methane. We also identified some possible ammonia, but we're not sure about that one. So we are flagging this for follow-up observations, but it's not going to be a priority for us. And follow-up observations are going to help detangle some confusion we had about the ammonia, and it'll also help us learn something about the inner edge habitable zone.
Okay, so last spectrum. So this one, we approximated the radius as being around 1,200 to 2,600 kilometers. It's 1 AU from the sun, so we think it's a terrestrial planet in the habitable zone. This spectrum was a little flatter, and it was kind of hard to find features, but we think that there's some ozone here at the beginning, and then we see a small O2 feature at 0.76 microns, then a lot of water features again, and then maybe some methane here at the end. So we are flagging this for follow-up observations. We think there are several promising biosignature features that we want to look more into, such as methane, oxygen, and ozone. We think it's in the habitable zone. It probably has liquid water based on that, on its surface. And then we have a big uncertainty on the size of the planet, though, so we would really like to put some more constraints on this by doing follow-up observations. And we would really like to do some more observations to potentially search for carbon dioxide as well.
Okay, well, questions? Okay, and the next team is going to be Exoplex Mantle Chemistry. You guys can get ready.
Can you explain the signature for haze? Can you explain the signature for haze? For haze at lower wavelength?
In the presentation for ExoEarth Finder, we were shown similar spectra that seem to have, covered now, but there's kind of a shoulder there, and sometimes it's quite clear that there's an ozone feature because it's quite deep. But it seemed like when it was a less deep feature that it was more attributable to a haze, but I would defer to anyone else on that.
Any other questions? Okay, let's thank the team again. Okay, so next we have Exoplex Mantle Chemistry Group, or Mantle Chemistry 1. And after them, so following this group, there will be Exoplex Mantle Chemistry 2. All right, hi everyone. We are Exoplex Mantle Chemistry Group 1, or MOLERATs. Mantle options for silicon/magnesium ratio applied to TRAPPIST-1. We are Megan, Sasha, Igor, Andrea, and other Megan. So basically our question that we were looking at is, how does changing the silicon to magnesium ratio affect the mass radius relationship of different TRAPPIST-1 planets? So the method we use is we vary the silicon and magnesium ratio between 0.6 and 2 in terms of mass ratio. And all other compositional variables were fixed to a bulk Earth ratios as shown here on the slide. And we tested this on TRAPPIST-1 planets using Exoplex, which is an awesome code where you can basically give Exoplex a input composition as well as either a mass or a radius, and it can give you the other variables back.
So as Megan said, we varied the silicon magnesium ratios for all of the TRAPPIST planets, and so from TRAPPIST A to F, TRAPPIST-1E was a success. It matched. We were able to match the radius the best. But however, all the other planets were failures. So
Yeah, so basically what we found is, unsurprisingly, changing the mantle composition doesn't have that big of an impact on the actual mass and radius you get out. That's because we're just changing between silicon and magnesium. Silicon has a molar mass of 24 grams and magnesium has 28. And so they're not that big of a difference when you compare to other things like water, which is 1, and iron, which is 56. So these two blue lines here show mass radius relationships for the lowest and highest silicon to magnesium ratios that we considered, and you can see they do pass within the range of TRAPPIST-1E, but they don't really get anywhere near the other planets. So in order to explore a bigger range of densities, you have to mess with either iron or water. So we messed with iron.
So for the second part of this project, we changed the, like Megan said, the iron to magnesium ratio, from anywhere between 0.1 and 0.9, thereby making these planets out less dense. And this is where we first start to see some success with TRAPPIST-1C, where our models match for ratios below 0.3. However, planets B and D, their chi-squared is still far above 1, and that leads us to conclude that these planets, we need to add some volatiles to these models to match these planets. Next, let's look at the other two planets. Here we have much better match for all three. Well, 2.5. Planet H in particular is a match for molar ratio 0.4, so roughly just under half of Earth's bulk ratio. And planet S, it is also 0.4. Now, originally, we were going to say that planet G is a success because the chi-squared falls below 1. However, it's just for molar ratio 0.05. So you're essentially taking out all of the items for a planet, which is probably unlikely. So this planet might as well need to add some volatiles to match this one.
Okay, so this is another version of the plot we showed at the end of our silicon magnesium ratio results, and what we've plotted here is the maximum and minimum iron over magnesium molar ratio as well, with a fixed silicon magnesium ratio of 0.9, and you can see that we get a much cozier looking range from the purple lines and the blue lines that put us a lot closer to the sort of low densities that we see for the majority of the TRAPPIST-1 planets. And the reason for this is the really big difference in relative molecular mass of iron and magnesium, which allows us to have about like a factor of 2 change in their mass versus the really small change if you're just switching out magnesium for silicon, which is only 4 relative molecular mass units smaller. So all our fits are generally better in the loosest sense of the word, but we still can't explain at least 3 of the planets very well with the variations in iron and magnesium ratio. But something that's really important that I feel like we've demonstrated here is that it's really interesting to see what you can't do to match the radii. So in this case, we can see that
changing mantle chemistry has a really small impact and is unlikely to be the reason behind the low mass radius, the low density of the TRAPPIST-1 planet. And then moving on to some of the other groups who will be looking at volatiles and changing some other parameters. But it's also important to remember that we're very unlikely to get constraints on mantle chemistry for any exoplanets other than indirectly through like atmospheric composition. And I would like to finish by saying MOLERATs in the TRAPPIST-1 system, it's more likely than you think. Thank you very much.
Great, David, thanks.
So when you're changing the iron to magnesium ratio, what exactly are you changing structurally in the planet?
So basically, we weren't changing, there is a way that you can change the amount of iron that's being incorporated into the mantle, but we weren't changing that, we're just adding more iron. So basically, we're changing the core mass fraction, making the core bigger and smaller.
And then your best fit iron to magnesium ratios, is that a high value, or is that a particularly low value or a particularly high value? So how does that iron to magnesium ratio compare to, say, the Earth, and then other things we may have talked about?
I believe there was a paper by Cayman Underborn that said that for the solar system planets, it's about 0.7, so this is a lot lower than that. So yeah, maybe not realistic.
Other questions? Okay, all right, well, let's thank the team again. All right, next up we have Exoplex Mantle Chemistry 2. All right, and after them, we will go back to Exo Earth Finder Group 1. Okay, so you guys are up next.
Right, so we're Team Irony.
The most important part.
Yeah, also a good start. Wrong way.
I know. Are you done?
Yeah, we're Team Irony, iron mantle chemistry. It's very important to include all letters in your acronym. And remember that N is in mantle and not iron. So we are Per Calisonar,
Rodolfo Garcia, Will Meissner,
Miguel Ángel. As a result of the data, we found the next physical effect. When we added iron into the mantle, directly the nucleus radius increased. And because the density of the mantle increased also, the radius of the planet increased. Decreased. Okay, when we take iron from the nucleus and pass through the mantle, the radius of the planet decreased.
So this is what happens when we there might be so we actually found that for almost all of our planets, none of them were consistent. So this is our model. The blue dots are our model, and the black squares are the measured values. And this is for putting no iron in the mantle. And we found that we could only reproduce TRAPPIST-1e all the other planets, we found radii that were too small for what they've actually been measured to be. And as Miguel Angel said, if you increase the amount of iron in the mantle, you actually decrease the radius that you get. And so essentially, putting any iron in the mantle would make our fits just worse.
So this just kind of shows that if you take iron from the core and put it in the mantle, as you increase that amount that you put in the mantle, it just keeps decreasing the radius of the planet that Exoplex gives us, which means that, you know, since we underestimated the radii in the first place, with no iron in the mantle, putting iron in the mantle is just going to continue that trend of underestimating the radii. So it's not a great thing to tune specifically to increase the radii.
Yeah, then we can see the error when we increase the fraction of iron in the mantle, just is increasing and increasing.
So after that, we had a lot of time, so we thought, let's take the mass uncertainties in the TRAPPIST planets and see if we take into account those uncertainties, can we reproduce their radii? So for some planets, like TRAPPIST-1c here, we did like a sort of Markov chain, Monte Carlo, no, just Monte Carlo, simulate, like drawing mass samples, calculating, you know, using Exoplex to run those mass samples is very quick. But even with that, you can see that the sort of mean radius that we get out doesn't come close to that black dotted line, which is the true radius, and then those two green dotted lines, which are plus or minus 1 sigma for the true radius of TRAPPIST-1c. But we get a little closer when we take into account uncertainties.
Yeah, and when we run this for the TRAPPIST-1e planet, which already had a good radius, then it doesn't really matter what iron fraction we use. We can reproduce pretty good true radii in any case.
And so just to summarize all that, when we experimented with changing the amount of iron in the mantle by taking it out of the core, doing that alone could not reproduce most of the TRAPPIST system. And so that leads us to a similar conclusion that the other mantle group had, that changing mantle composition alone isn't going to solve the issues with the TRAPPIST system, and that we probably need to either modify the core chemistry by adding lighter elements, which we're just going to talk about, or change other composition or add volatiles to different parts of the planet. Increasing the amount of iron in the mantle, as we talked about, decreases the radius because it decreases the core size and increases the mantle density, but the effect is pretty small. And TRAPPIST-1e, which has the density closest to Earth of all the planets, is only slightly sensitive to changes in the amount of iron in the mantle, and we could reproduce its radius essentially with any mantle iron fraction that we chose in our parameter space. And with that, we'll take questions.
I did not get this point, that how is it that taking iron out of core and putting it in mantle decreases the radius of the planet? Because iron will be more compressed if it is in the core. If you're spreading it around in the mantle, isn't it less compressed? And so doesn't that, or probably, sorry, probably I'm missing something. Probably it is not that straightforward. But.
So basically, I think what Exoplex is doing is taking, like, let's say you have a constant amount of iron in your planet. If you take some of that constant amount of iron and put it in your mantle, your core gets a little smaller just because now there's less iron in the core. And then your mantle gets more dense because there's iron in your mantle, which means that your mantle will get a little smaller for the same constant mass. I think that will also still put more pressure on the core because your mantle gets bigger, your core gets a little smaller. So I think it does compress your core a bit.
you're decreasing the radius of the core, but you're putting that mass into the mantle. So you're increasing the density of the mantle, but you're also increasing its mass.
But it has to do with how, oh, thanks. So it has to do with how we set up the model, and that we use shells of constant mass. And one of the things in the equation of state that we didn't talk about is this concept of compressibility, and what certain minerals are easier to squeeze than others. And mantle rocks are easier to squeeze than iron in the core. And so if you have a constant mass shell, but your mantle is more compressible, even though it has iron in it, you will compress that to a smaller size, so you'll get a smaller radius, even though you've conserved mass. That's like next level.
Thank you.
So that was a really good question. All right, who has another one?
TRAPPIST-1E said has the closest density to Earth. How close? Because we were the water group, and we've got some stuff to say about TRAPPIST-E.
I can't remember it exactly, but it's like 1.024 Earth density.
Okay, thank you.
Okay, any other questions? All right, it's gonna be a smackdown later. Okay, all right, let's thank this group again. Okay, Exo Earth Finder Group 1, you're up. And after this group, it will be Exo Earth Finder Group 3.
What do we have to hit for advancing that? Okay. All right, great.
All right. So pretend no one's done this joke before, but our acronym there. So I'll point out that we would be group 1, so we do have priority on this. So to jump into this, so we had 4 spectra to look at, and what we have here is this is normalizing them all by removing the effect of the semi-major axis. And so they're all around the same star. So at this point now, we just have as a function of wavelength, we have the flux ratio, and sort of the 2 other things that are sort of tied into this equation. Really, we have concerns about what the albedo is and what the radius of the planet is. And so rather than try to make any assumptions on that, we sort of categorize these based off a normalized version of just saying that the smallest albedo times radius planet object is 1, and look at the relative numbers. And so when we do that, and note that this is a log plot, so there's a very big range in these fluxes. We can sort of quickly categorize these comparatively, that the bottom 2 here, we think are both roughly terrestrial. We are being slightly gutsy and saying that the brighter one is in fact possibly smaller and more like Venus. But again, that is very much, there's an relation between the radius and the albedo, and we're not trying to solve that here. As we go up, we have what we think is, actually should be potentially not an ice giant, but a giant. In this case, it's in at 1 AU, so this is more of a temperate Neptune. And then the furthest one up, which is a Jovian planet at 5.2 AU, which sounds suspiciously like a Jovian planet that is Jupiter. So we'll go into the breakdown of each of these independently. There's this one.
All right, so planet 1, again, if you go back here. That's the one on top. Sorry. Okay. So planet 1, we're going to look at planet 1 first. That's the one that's about 20 times larger than radius-wise, larger than the smallest one. And it's sitting about 5 AU. Again, like Mike said, it's probably, well, 5 AU, that's about the same distance that Jupiter is from the Sun.
This one's the 1 AU.
Oh, no, this is planet 1. Right, this is planet 1. Okay, that's just more than it. Okay, so this is sitting at 1 AU around a Sun-like star. And this is the one that's like 20 times, yeah. So it's about 20 times larger than our smallest one. Oh, sorry. I keep looking at the green. Okay, so we're looking at the first one is the blue one, right? So this is the one that's about 6 times larger than our smallest one. It's sitting at 1 AU. So we assume again that this is probably some sort of giant planet. We're not assuming it's terrestrial at this point. Some of the features we observed, there's definitely water features in the spectrum, and it's not super clear whether there is some ammonia, possibly some ammonia at both wavelengths there, 1.95 and 2 microns, which would be this region here, but it's difficult to say because the H2O features are so strong. So there's a lot of water. This is a giant planet sitting at 1 AU, so there's water vapor in the atmosphere, but it's unclear exactly in terms of anything else. It's in the habitable zone, but it is a giant planet. I don't see any kind of any kind of disequilibrium in the chemistry, so not a likely candidate for life.
All right, so moving on to our second one, and this will be the one that we'll get the most aggressive in calling what we think it is, we think that this is Hazy Archean Earth. It's at 1 AU, which is good to be an Earth. And so we do have a couple features to show up. We have the haze close in. We have some features that maybe methane and water further out. This also looks relatively. We think this looks relatively familiar for anyone who was in the lecture portion for the all hands, for the hands-on, because that was one of the slides, and that Hazy Archean Earth looks conveniently similar to what we have. So a much better labeled version of this one. And so because of that, we would put this at an extremely high priority follow-up. So this is everything that one would want to have for earlier life studies. Going on to our third one, our Jupiter analog at about a Jupiter distance. And so this is too far out to be habitable. There are some things that show up in the spectrum we think possibly methane. There's a few others that may be in there a bit weaker. It's a little bit trickier to tell whether or not those are strong signals or whether or not we're fitting whatever we want in there at a certain point. But so in this case, because we do think this is a giant planet, if we assume that the last one was an Earth with an Earth albedo, if we assume then that this one is a Jupiter with a Jupiter albedo, it's about 11 times the radius of the Earth, which is about the same size as Jupiter to Earth. But so because this is further out and it's a giant planet, this would be fairly low priority if we're concerned about signs of life.
All right, and to our last one. Again, this is we propose this is a planet that's more like Venus-like. And again, this is sitting at 0.7 AU, which is also the distance of Venus, about the distance of Venus is sitting from the Sun. And the features, some of the features are interesting, which also makes us believe that this is something close to a Venus analog. We do seem to have indication of some sort of haze here. And We do see features for CO2 right there. It's unclear whether there's possibly some ammonia, but it's not super clear. And also, you're getting here in the thermal radiation from the instrument, so I guess we shouldn't really be looking too much. We shouldn't read too much into that, the data there. It's sort of, I guess it's on the inner boundary of the habitable zone, so it's in a good location, except that we don't see any kind of bio signatures. In fact, there's possibly some carbon monoxide, which in combination with CO2 would be an anti-biosignature. And in terms of that case, I was just wondering, like, I mean, I don't know actually if we can measure these other molecules there, the disulfur oxide and disulfur dioxide, but those are possible absorbers of UV light. So anyway, that's all about in terms of what we found in this planet.
Questions? Okay.
Yeah, so your first plot, the way you handled that, by, correcting them all to the same semi-major axis and then plotting the sizes as relative to the smallest, that's a very good, that's a good idea. That's a good way to do it. You resisted the urge to overinterpret the sizes of the planet in, when you can see that it is in fact degenerate. So good job. Good job on that one.
Can I reverse this into a question? When dealing with this normally, is there a particular wavelength that should be looked at that is likely unaffected to actually look at what you would expect the actual relative values to be, so you're not worrying that you're seeing a dip because of something absorption, for example?
Well, I will say, I mean, as you can see here, there is a degeneracy here, and it is difficult to pull out planet radius from direct spectroscopy. The person who could talk about how well you can do that would be Ty Robinson, if he's still here, or Giada. Okay, Giada, do you want to comment? Yeah, what's the means? Basically, actually, I think I basically sort of understand it. Basically, it's kind of like what you did, or maybe a different team did. You look at your models and you compare to like what are plausible ranges of albedos in particular critical wavelength ranges. I'm not exactly sure which wavelength ranges are right. Vicky, okay, Vicky, maybe you should answer this. Yeah. Yeah. Although I will say that, the way you, I guess, to put it in a slightly different way, the way you get it is you think about what else do you know about what kind of planet this is, and then use that to help you narrow in that range of plausible albedos. So kind of take a, yeah. Yeah, I guess the other group can say how well that will work.
Okay, we need to move on. Thank you for that. Okay, thank you. All right, we have 4 groups left. Okay, so Exo Earthfinder Group 3, you guys are up. And after them is Exoplex Water Content.
I'm Alex, and these are my 3 colleagues, and one of them skipped out on the presentation, but he was very helpful in the analysis. So, pretty much the same format as previous groups. I'll begin with the standard disclaimer that what we have here are flux contrast, and that's the degenerate number. In these cases, we know the semi-major axis pretty well, but the albedo and the radius are pretty degenerate, so any estimate we give to the radius is accurate to a factor of 2 to 3, but good enough to tell whether or not it's very large or very small. And in all these cases, we have a solar twin at 5 parsecs, and we've imaged the planet at quadratures.
Okay, so our first planet we kind of compared to a Jupiter analog. You can see the lines highlighted in different colors that we identified. I think we see a haze in the shorter wavelength, and then the planet radius we thought to be about on the order of magnitude of about 10 times the Earth radius. So with a semi-major axis of 5.2 AU, that makes it very, very comparable to Jupiter analog, as well as the spectral lines that we identified. So that's the gas giant. It's not really a great candidate for habitability. We don't really see any obvious biosignatures.
Thank you. Right, so this was the second planet in our list, and if you're a fan of CO2, this might be the one for you. So as you can see there in the green, there's our various CO2 lines that we identified during our analysis, but we also identified the possible presence of a haze, highlighted in the orange. And also around 1.6 microns, we also potentially highlighted the presence of carbon monoxide as well, but it had a similar strength to CO2. I found it difficult to distinguish. So this planet is at a semi-major axis of 0.7 AU, and calculated the radius roughly Earth-ish size radius. So terrestrial-like planet with a somewhat Venusian-like atmosphere. So we put it kind of lowish down on the follow-up list.
I'm assuming most of you have watched The Parent Trap. It's about a little young Lindsay Lohan who lives most of her life, doesn't realize there's an identical twin of her out there. Little does she know there is. This planet we deem to basically be the Lindsay Lohan of our Earth, so call it the Planet Trap. The semi-major axis is just 1 AU, about a star that's just like our sun, so it already matches just like our own Earth. And its planet to star flux ratio is about 10 to the negative 10, which is equivalent to about an Earth radius as well. It's a very terrestrial, rocky world, and if you move left to right with me on the spectrum, you see that it's got the signatures of an ozone. It has your Rayleigh scattering. And then it's just rich with all of your biosignatures that you'd want for life. It's got oxygen, really nice water lines, some methane, and CO2. And so it's definitely worth following up. It could be the closest thing we've found to Earth so far, but I'm guessing it's probably fake data or our own Earth data. But let's follow it up for sure.
Okay, so here we have basically a very similar planet to our first one. This is a large planet, to say the least. Even if it's very reflective, I think it's going to be about Jupiter's size. So this may be slightly larger than Jupiter. Sort of interesting given the size of, say, hot Jupiters that we found to date. Typically seen 1.5 Jupiter radii. Again, we have very heavy absorption in the infrared, so it's kind of hard to disentangle which species are responsible for all the absorption. I think maybe I thought there could be some carbon dioxide in the spectrum too, but haven't included it here. And then I guess the one interesting thing I'll point out is the hydrogen fluoride seems kind of obvious based on the structure of these absorption lines. They have these little inverse peaks, which seem to correspond to gaps in the line absorption profile. So this is at 2 AU, I should mention. Altogether, maybe an interesting planet if you like gas giants, but perhaps not worth doing more observations than we clearly already have done. Okay, so that's all 4 of ours. In terms of priority, I think it's clear that our potentially Earth-like planet with a couple of very interesting biosignatures is the one we want to go after. Just to understand the diversity of terrestrial worlds and look at ideas like the habitable zone, we could perhaps do follow-up observations of our potential Venus analog. And then we think that the Jupiter and super Jupiter analogs not worth revisiting.
Questions? Everybody's getting tired. All right, somebody must have a question. Kevin?
Okay, maybe not.
Question on what I'll refer to as the Haley Mills planet there.
Sorry?
So when you say this is very much like the Earth, is this, since we've seen the Earth in various different stages, is this the current Earth or the Earth at some other stage?
Good question. I think if anybody here knows, a possibly more confident way to put this, it looks like a potential present-day Earth, something that maybe has evolved to the same level that we see here. My knowledge in atmospheres isn't quite enough to pull the age or some sort of a twiddle age from the spectra, whether or not one is being so comfortable. Got oxygen. Got oxygen. That's there. Right, so it's not an anoxide Earth. The water is presumed to be liquid just because of the temperature and the distance, but we see the formation of an ozone has probably occurred as we discuss that beginning part of the spectra. But for me, that's about all I can speak to.
Any other questions?
Unlike when
Good analogy. All right, let's thank this group again. Okay, now we only have 3 groups left. We're in the home stretch. Exoplex water content is next, and after them is Exoplex core chemistry, and then we'll finish up with Exo Earthfinder group 4. Okay? No?
Which mic?
Who has the slide in there?
Is it right here?
Oh, it's right there.
All right, let's see. Back for back, F for forward. I presume, yes, all right. You are. Okay, hello everybody. I am Sean McClote from the wonderful University of North Dakota. I'm a PhD student there. Do you want to introduce yourself?
I'm Domenico Barbato from the equally wonderful Observatory of Turin, Northern Italy, last year PhD student.
And we are Team Panache. Okay, yes. Panache is a watered-down version of beer, and since our team is exploring water content in the Trappist planets, a known type of beer, the name kind of made up itself for us. Dom has also come up with an acronym which he had to write on the board, but it makes sense why. It says pertinent acronym names are clearly arduous endeavors. So there you go. So we wrote our actual acronym on the board because it was arduous. Team name makes sense. It's also a brand of braziers, so I have to be very careful while Google imaging this image here. Okay. Exoplex water content. We had to turn the knob to increase the water fractional content in the Trappist planets, fix the mass measurements that they are obtained from TTVs, and see if we can fit the radius. So we turn the water knob, increase the radius of our planet balloons, and see if we can get them to fit. And we went planet by planet, and here we don't, in the code we did decimal points here, we just give them as percent. So I'll take it away, and you can correct me if I stumble here. All right, Trappist 1B. So on your right, we have the range of radii that we obtained by changing the water content from about 0 to 50%. And you can see between 0 and 50% water content of the planet, we're able to fit the radius measurement. We then explored in that parameter space which values of the water content we're able to obtain a less than 1 chi-squared value. And so that dips between here. And so we just kind of eyeballed it on the graph here. This is chi-squared of 1, below 1. It's between about 10 and 23% weight water content for TRAPPIST-1B, which is quite a lot. TRAPPIST-1C did the same procedure here, varied. Our third team member, who I didn't introduce, James Mancini, who I stuck out early. He was,
okay.
yes.
What's one thing we want?
Yeah, he helped us with these planets. He did TRAPPIST-1C. But you can see as well, this is the range of parameter space. So changing the water content changes the radii fit by quite a bit. So it's very easy to fit radius just by changing just the water content, which is a takeaway from this assignment. Again, the under chi-squared of 1 is between about 2.5 and 12% water. TRAPPIST-1D is same deal, wide range of parameter space between underneath the chi-squared of 1. We get a range between 13 and 24% by water. And for this planet, we just pulled out the fact, just quantified how much the radius changes by changing a certain amount of water content. We quantified that to saying about a 5% change in the water results in about a 2% change in the radii, the radius of your planet. Can't have more than 1 meter. So that's it. TRAPPIST-1E. I made this sound really ominous before. I don't know why I sounded so threatening. But it's an oddball of a planet, to be sure. Changing the water content, the reason this is so vast is because we actually explored the parameter space between 0 and 75% water content just to see where it would go, and it went up a lot. We had the chi-square fit value was consistent with 0 to very low, from 0 to 1% weight by water. So I have thoughts about that from the other group as well. TRAPPIST-1F, same deal, wide range parameter space, so low chi-squared, 5 to 15. And for TRAPPIST-1G is between 12 and 22% water in the range. Again, full parameter space was explored, so that you get a good sense of that range there. Okay. Oh, and 1H. So many. So wonderful. Between 3 and 16% water for TRAPPIST-1H down here, so a good range of data space explored. So, oh yeah. Well, we looked it up after we fit these ranges. So this, yes, we did the honest thing. And she did after the fact. No. So we looked up this plot from Kamen's paper in Nature, updated compositional models of the TRAPPIST planet, where this is plotting the same fit of values that are fit below a chi-square value of 1, and just eyeballing it and just changing just the water content of the planet. The radii is a roughly close match to the ranges that Kamen found in his paper. I didn't actually read the fine print in your paper, so I think there's something like a degeneracy between water content and changing the core size. Yes, thank you. Yeah. So TRAPPIST-1E is very interesting. We went to the next step in the assignment with that one, where we included the uncertainty in the mass estimates for TRAPPIST-1E and let that vary while we also tried to fit for the radius by changing the water content value. This is using the minimum value for the chi-square fit and the maximum value of the chi-square fit, that range where it's beneath 1. And this is where we were looking at it, and the bell rang, for lack of a better term. It doesn't, if I were looking at this, I would say that this is not great. This is a pretty wide range of values, a wide scatter, perhaps, for the radius of the TRAPPIST-1E planet based on the uncertainty in the mass, which is pretty large. That is where we are done, and we'll take your questions. Thank you.
Okay, somebody needs to ask a question. Right, Aki.
So would you stick your neck out and declare that TRAPPIST-1E is a rocky planet?
I was thinking about this based on the other group's assignments, and the Earth percent water weight, I'm not sure exactly what that phrase is, but Earth is 0.05% water. So TRAPPIST-E having such a low amount of water, and having such a wide range of possible iron core contents, as from our esteemed colleagues in group mantle groups 1 and 2, suggests that it could be Earth-like, perhaps in bulk composition. In fact, the starting parameters for the other parameters from the other groups was to assume it was generally Earth-like in bulk composition. So I would say, yeah.
I definitely stick my neck out and say it's rocky, but whether it's Earth-like, you know, we just saw from the other two groups that a lot of compositions are consistent with TRAPPIST-1E, and so we don't know the consequences of those, all that degeneracy. So even having a smaller core, how that would change the evolution of TRAPPIST-1E. So
the Stephen King technique, it could be consistent with having Earth-like amount of water by weight, perhaps. Or none, yes. Hello.
So when you have like a 10, like many, like, 10 to 20% of water, so where do you have water in this calculation?
Where is it? To be honest, when I was producing these plots, I actually turned off the function that plots what the core radius and mantle radius and surface pressures and densities look like. But I would assume that you can't have 20% of your mass of water all on the surface. That seems not possible. So I would assume that there could be a surface, perhaps surface water, but most would be in hydrated minerals throughout the mantle. That's just sort of a sounds reasonable. I'm just throwing that out there. I thought about getting this question, and that's the answer I came up with just thinking about it.
Does your teammate agree?
Help me.
Oh, no, actually, it sounds reasonable. I completely agree. Seriously, I think 20% water mass. What was 20? What? I mean, so, I remember a movie called Waterworld, and I do not want to remember that. So, no, I mean, I actually think that with such a high percentage, most of the water will be on the ground, and so yeah.
Oh,
but realistically, according to the model in the code, of course, but if we wanted to compare with the realistic distribution, probably not such a good idea. I think 20% of all the mass of the planet on the very top. Oh, yeah.
For context, Europa is 7% water by weight mass. Okay, thank you.
Okay, let's thank this group again. All right, next up is Exoplex core chemistry.
So we are the core chemistry in the core chemistry group, Exoplex as well, or Quarry. I have the honor of introducing my esteemed colleagues. I am Daniel Yahalomi. I'm a postdoc at the CFA. We have David Rice, who's a grad student at UNLV. Surangama Rukti, who is a postdoc at the CFA. Amy Glazier, who's a grad student at UNC Chapel Hill, and Akash Gupta, who is a grad student at UCLA. And now they will speak some more.
So what we want to do with the way we use Exoplex is we want to figure out, so what's the composition of the core of each of the planets of TRAPPIST-1? Now we know the mass and the radius, so if we want to know the composition, why not start by finding the radius, which we already know. It's less circular than it sounds. So what you do is you vary the fraction of elements that are in the core. In this case, we specifically varied the fraction of oxygen in the core of each of the planets of TRAPPIST-1, holding the masses constant and then backing out, okay, given this composition, what's the radius for each of these planets? And then how does that radius compare to the actual radius that we know for each of these planets? For the idea is that if we can match the radius that each of these planets actually has, then this composition that yields that radius is most likely the composition of the planet's core.
So as Amy mentioned, that we try to tune the oxygen content in the core using exoplex. And what we do in our group is we basically tune them all together in parallel from the range of 0 to 50%. And so every 5%, and we found that in this range, most of the planets fit within this range except for the E planet. And every 5% change in the weight of oxygen in the core according to 1% change of the radius of the planet.
All right, chi-squared plots. So we're pumping oxygen into the core. Really, what came into doing is tacky, and that no, it's really good. Is we're just changing the core's density, basically. So we're pumping. We know the Earth has a. I just looked up a review paper. I don't really know this off the top of my head, but it's a 5% density deficit in the Earth, and we think that's like 5% by weight silicon and 1% oxygen, 2% carbon, and 2% sulfur. People have some guesses, but it's really just guesses. So we have an Earth line on here. We've changed the x-axis. We're pumping in oxygen, but we've done, don't quote those numbers, but we've changed it to a molecular mass. So of course, the molecular mass of iron is about 55. We can see the Earth line there. That was just a back of the envelope calculation. So we've started these things near or 0% of oxygen in the core, and then Earth. You can see these things take a lot more oxygen in the core than the Earth does, so we can zoom in on those. So they just zoomed in on that last plot, and you can see that we have to make the core quite a bit lighter to get all the way at the minimum of the chi-squared. But if you're uncomfortable with that 20% of volatiles of water on the surface, you could change it, just a little bit, get closer to the chi-squared of 1, 42 molecular mass of the core isn't crazy to think about, I don't think. So that could just decrease that amount of water that you need for those planets. Yeah, just want to look at that in color.
So all these groups which have been working with exoplex, what they basically have been doing is they have been varying certain parameters that define the planet's composition, and have been trying to figure out if the results match with the observations or not. But what we should remember is that exoplex is a great tool, but we need to be a bit like intelligent about like really how we use it. So our next plot basically shows that quite a few of our results are actually not right. So even though we do get consistency with what we are observing, but they might not be right. So what this plot is showing is how the density, which is the y-axis, changes with the radius of the planet. So basically this is showing how the density changes with the depth in a planet, starting with a low density at the surface, and this is when the mantle core transition happens. And so this is how the density profile looks when the whole core is simply made of iron. On the other hand, if you add like 50% oxygen or an equivalent material which makes the core lighter, then this is what the results looks like. So in this case, what you are clearly seeing is that the mantle is actually denser than the core, which is not really like physically possible. So on the ending note, I would just like to emphasize that we just need to be careful about how we are using these tools, which are like really great in figuring out what these planets are made of and what is happening in these planets, but we just need to be a bit more careful. Yeah. Thank you.
Okay, questions? That was a really good, okay, we'll do after my camera.
It seemed like on your chi-square plots that, again, TRAPPIST-1E looked different from the others. Is that right?
We've talked about that enough.
Yeah.
We don't need to talk about E anymore.
Well, I actually think it's interesting when you see a planet that looks anomalous in several different ways. and to several different approaches. So what did you see for that one? I couldn't, you didn't explain the chi-squared plot.
So E, like we've talked about, has to be pretty much, you can't do anything to it to increase, without incorporating the error bars and stuff, you can't do anything to increase the radius.
It still lies within the error bar. So it could be that could be improve our like observation. So this is, even if it does lie within the error bar, it could be that it is purely RN, like the core is like purely RN that explains the observations and without any water layer at the very top. Or what could also be the case is that it got stripped, like it got stripped of its atmosphere because of some violent like episode that happens in its history, and so because of that reason the core is in fact like more compressed than what it should be. Perhaps the way it is for Mercury. I don't know what exactly it is going to be, but maybe something like that.
Can you go back to the chi-squared plot? Thanks. So this is actually really interesting, and I've never actually ran these calculations for the TRAPPIST-1, and so this is great. I've never seen this plot before. And I will say that 30, a molecular weight of your core of 30 is probably absurd. That may be because these are compositions with iron that we've never really thought of in the lab. And so we actually don't know what, we kind of did a trick where we changed the molar mass of the core, because I kind of threw out that the equation of state shouldn't change too much. But now at these, if the TRAPPIST-1 are consistent with this kind of composition, it might be where we have to start taking into account differences in equation of state and get new measurements. So while this plot may be ridiculous to someone who kind of thinks about this stuff, it really does point out very clearly that these are chemistries that we need to be thinking about, because it's consistent. So yeah, I really like this plot. Good job, guys.
Maybe someday we'll drill that deep and the core will just like come.
Yeah, the rocky cores is a cool idea. Let's explore it.
Just on that point, there is not necessarily, so the TRAPPIST system is probably a little small, but there's no reason you actually, for larger planets, expect the planet to differentiate, that actually the timescale of differentiation can be longer than the age of the system. And so maybe not so ridiculous, but definitely with this equation of state.
Yeah, well, I guess these are not quite, so I guess when you guys did this, and the core chemistry one was the one I cheerleaded as kind of the cool new thing, so would you have thought of this as astronomers to start changing kind of esoteric chemistries like these with your mass radius models, or would you have jumped right to something like water? Because the light elements and cores are possible.
No, I would never. Yeah, I mean, 20% water made a lot of people uncomfortable from the last group. So if you're uncomfortable with that, this was definitely like, even if you don't have to go that far.
Before this workshop, no, that would never have occurred to me.
But something fun can be developing to the atmosphere to see how that makes things. Yeah, all of them, definitely.
Okay, great. Let's thank this group again. All right, and last but certainly not least, EXO Earthfinder Group 4, please.
Hi everyone, I'm Jake Taylor. I'm a PhD student at the University of Oxford.
I'm Jager. I'm a PhD student at the University of Maryland.
And I am Andrea. I'm a PhD student at the University of Berlin.
And probably we have the less creative name, but it's probably the more colorful of all. So we are the extra finders. Um, okay, so I'm gonna start. I'm gonna present you the first spectra that we got. That's probably group number 1 already presented as well. So I'm gonna be quick. So basically, I looked for which spectral features are in this wavelength range. So I realized that probably this is CO2, and then you can see here at around 1.4 and also 1.6, and definitely a big one here at the 2 micron mark. And also this flat one here, well, I realized that could be clouds, and as people have been pointing out, I just learned also that this could probably be because of haze. Yeah, so just to answer the questions of that were formulated, we have that is the planet large or small? Well, it depends on the albedo we actually choose. So I just tried for a couple of them because I figured that if it is CO2 dominated, it might be something like more or less like Mars or Venus. So for that, for the Mars geometric albedo, I got something of around like an Earth radii. And then for the Venus one, I got like half radius of the Earth. So what molecules are present in the atmosphere? I just told you it's CO2. What kind of planet? Well, I gave you a thought of this. So probably it's like Mars, Venus-like atmosphere because of the molecule that is more present. And about the size, well, it depends. No? Well, it could be Earth size or sub-Earth. Is this a habitable planet candidate? Probably not, because the distance that we got was 0.7, and it was defined that the radius or the range would be between 0.75 up to 0.9, something like that. So probably not. It's close, not quite. Is it rocky? Yes, but for example, this one is still small, so it would mean that it's habitable in the whole sense, but this one, well, it's still rocky. This is not the effective temperature. This is the equilibrium temperature that Kentang, who's not here, calculated for us. So it was around like this is the planetary equilibrium temperature. It was 328 Kelvin, so probably it's like at the limit of water evaporation, but maybe because of the clouds, we don't see any kind of feature. Are there any potential biosignatures? No, sadly, not at least that I saw. And well, is this like good for follow-up? Well, why not? It's always cool, but it's also close, it's nearby. There's also ratios, so probably. And yeah, I'll leave it to the second one.
Right, you may have seen this spectrum before, implying that Lindsay Lohan is part of a triplet, not a twin. But anyways, so you see some strong ozone feature here, but you can see that the scale is negative, that the flux ratio is negative. So let's blow this up. So here's the blown up version. So you can clearly see some water features, the big water bumps. And since this is high resolution, we can also take methane independent water as well. And then there's some tiny bits of very narrow lines of O2 as well. So we have water, definitely, ozone and O2 and stage 4, probably. And if you calculate the radius, depending on your assumed value of albedo, and here I use a value between 0.3 and 0.7, corresponding to Mars and Venus, you get a Mars-sized planet. So this is quite a small planet, but very Earth-like, obviously. And then using the semi-major axis of 1 AU and a Sun-like star, we calculate the equilibrium temperature for a black body-like planet of around 170 Kelvin. So this is the minimum temperature. So with the atmosphere, it probably will be warmer than this, probably at our temperature. So is it a habitable planet candidate? It's 1 AU around the Sun-like star, so definitely. Are there any potential bias signatures? We have ozone, O2, and stage 4, so absolutely. So should we flag it for follow-up observations? So first thing I would do is do an actual retrieval on the spectrum rather than just by eye. And then I will follow up for mass observations. We have precise gravity and surface pressure measurements. And then since this is a close target at 5 parsecs with very strong biosignature potential, we should follow up for other potential biosignatures such as seasonality. So in sum, we found a Mars-like planet with water, But if this workshop's taught me anything, you should be cautious to conclude that there's life on it.
Okay, next up, we have what Quentin analyzed. He's not here, so I'm going to do it for him. Basically, this is kind of like a Jupyter analog. He assumed it to have a beta of 0.5 for his calculation. And there's a bunch of absorption features that he found. And so he's color coordinated them. So there's water, and then methane, and then clouds and aerosols. By calculating the equilibrium temperature, he found it to be 160 Kelvin, so it's pretty cold, and no potential biosignatures. But I guess water is a biosignature. And he thinks Jupyter are really cool, so we should follow it up. That was his reasoning. Here's my planet. I used an albedo in the range of 0.3 to 0.7 like the rest of the group, so we could get a rough idea of the radius size. And I find it to be from 1.7 to 2.7 Earth radii, which is too large to be a rocky planet. Next, I want to show that the different molecules that I can see. So this is just by eye. First, you see some broad water features, but in this region, we also have methane, but we don't see it by eye because the absorption of water is stronger. So we probably want to do a retrieval to try and tease out those features. Next here is this little absorption here, which overlaps both CO2 and CO. So wasn't sure what that could be, but here is definitely a CO2 feature. Here we have a nice Rayleigh slope, so I put a cute rainbow just to show that it's like the sky. Here is a lovely ozone feature. So here we see ozone, and here also is an O2. I think that's O2. Could be O2 or water. Aki is like, no, it's water. Okay. What type of planet is it? I think it's a Proterozoic Earth atmosphere. Just considering the things that we see, and also because of the ozone here. And then I calculated the temperature to be 265 to 327 Kelvin. So I think it's a Proterozoic Earth atmosphere, but it's too large to be an Earth-type planet. So it's too large to be habitable, according to Rogers 2015, but the temperature is consistent to have liquid water on the surface if it were to be rocky. So these are the biosignatures I talked about, and I think it's great to follow up, firstly because it's so close, it's 5 parsecs. That's a great target. And here, if we look here, we have the ratio of the planet flux to the star flux to be 10 to the minus 10, which is perfect for the directly imaged of Earth-type planet. And if we also look at the error bars, they're tiny, so this is a really great signal. So this would be great to just like follow up, get some temporal variations and see what we can see in the atmosphere. And then again, like group 1, I guess they showed it first, damn it, but I also saw in the slides that we have seen this already. And as you can see, there's the ozone here and then the features are the same, but they look more washed out here because this is a perfect model and this is observation. So that's our talk.
Okay, questions for our last group?
I really like that you think like an observer. So it's great SNR, no matter what it is, let's point at it. So that's a good approach. So that maybe also goes to the other team. So if you could choose one of the other parameters to be given, which one would it be? So would you choose to get like a perfect albedo value or perfect mass or temperature? What would be the best? If you could choose just one other measurement that you have a perfect value of, what would that be?
I would argue that albedo could be inferred by fitting for the composition. So in your retrieval, you could include albedo as your parameter, but mass is somewhat less determined from the spectrum alone, and that determines your surface pressure, which also has a huge impact on habitability and whatnot. So, and it could be detected by other methods such as RV, which is an easy method. So arguably, I would say mass is the parameter one in addition to what's been given.
What do you mean by too big to be habitable?
Oh, so basically, there was a study conducted by Rogers 2015. It was part of the lecture that we had. And basically, if it's 1.5 Earth radii or larger, then it tends to be more on like the gaseous side. So, I mean, it's just not rocky. And so on the surface, there won't be life or like habitable features. But I mean, that's all I interpreted from that.
Any other questions? Yeah. Do you guys want to see the answers? All right, let's thank this team again. All right, good job to all of the teams. All right, Aki is gonna show the answers. Okay, those are the answers. Okay, so I tried to take some notes on each group as we went through. I must say, oh, so this was a lot of fun. So thanks a lot. I must say, it's obviously very tempting to overinterpret the radius that you think you have. I guess that's a warning again. And so kudos, I would say, to the groups that recognized it was degenerate and tried to resist the urge to take it too literally, because I think that led some groups in kind of like off the rails a little bit, and it was specifically that bit about the radius. So, like for example, I think group 5, what they had were lower limits on their planet radii. So they said that the modern Earth and the Proterozoic Earth were not candidates for follow-up because they were too small, which is disappointing because those were actually, I mean, when I should point out here, this Earth, this label here, that's modern Earth. It's identically modern Earth. So, and Jupiter, yes, that's identically actually Jupiter's observed. It's actually not even a model. It's observed spectra, high quality observed spectra of Jupiter that have been noised down. So let's see. I think group 2 correctly flagged Archean Earth and modern Earth for potentially habitable possible biosignatures. Good. Missed the CO2 in Venus. Did flag it as small rocky. So this is another lesson about it's easy to misidentify molecular features. So this is another thing that happened a lot too that surprised me a little bit, is that I think multiple groups identified methane and Jupiter as water actually. So again, there are a lot of features of both of those molecules running throughout this whole bandpass, so you just gotta be a little careful there, I would say. Okay, like I said, I liked what group 1 did about normalizing to the smallest planet. That was a good way of doing it. And you got the cloudy, warm Neptune and the Archean Earth, yeah, and it's like I said, I didn't make this too hard for you guys, and yes, I did actually show you some of the models that were used, in my presentation. But let's see. Interestingly, a few groups actually kind of like got the right answer for the wrong reasons, but that's okay. And incidentally, if you see a feature and you think it's hydrogen fluoride or fluorine, it's not. So, okay. Yeah. So that was kind of what I was trying to hint at in my presentation about. Think about plausible molecules in the sense: is it made out of cosmically abundant elements? Let's see. I'm not sure which group it was, but maybe it was group 4. One group in particular. I have to check my notes.
somebody did a good job of actually flagging clouds and hazes, so good job. And although, so group 4, that last one there, again, this was the thing, yeah, that was, so that was actually modern Earth and Proterozoic Earth. So again, I think you over-interpreted your radii, making the planets too small. So, but you still said it was a Proterozoic Earth, and you flagged it for follow-up. Great. So, right. So, let's see, what other thoughts that I have there? I'm not exactly sure why you got a too large radius for Proterozoic Earth. Too small. It's funny. It's too small radius for modern Earth and too large for Proterozoic. I'm not sure why that. Oh, okay. Okay. I'll have to go back and look at that more carefully. But still, got the molecular IDs correctly, so still correctly flagged it as what it was. So, and the right atmosphere. So anyway, so that was interesting. Thanks a lot. That was fun.
Okay, we have almost reached the end. This is Kevin Hardegree-Ullman. He is currently with us at IPAC here at Caltech, and he's going to give a minute, maybe a minute and a half, on the IPAC Visiting Graduate Student Fellowship that we have. And then I'm going to run through very quickly some closing slides, and then everybody can go and enjoy the rest of the day. Kevin.
Thank you, and thank you all the organizers for such a wonderful week of programming, and thank you all for staying until the very end. Save the best for last. I'm advertising the IPAC Visiting Grad Fellowship, partly because I'm at IPAC, but also I was an IPAC fellow 2 years ago, and it was probably one of the best and most fruitful experiences of my entire graduate career. And so head to this website if you're a graduate student or if you have your own graduate students. There are, I think, 16 projects this year that are being advertised. It's a 6-month paid fellowship here that starts roughly around February of next year. The application deadline is August 23rd, so you have a little over a month, and it's one of the easiest applications you'll ever do in your life. You fill out a letter of interest saying which projects you're interested in and how you sort of fit in with the projects. You submit your CV, and you have one letter of reference probably from your immediate advisor. There are right now 6 exoplanet-related projects. Here's a list of them from 2 microlensing projects, the role of binary stars affecting formation and evolution of planet systems. There's a direct imaging project, and I'm actually co-leading a project about atmospheres of hot Jupiter. So if you're interested at all in the hottest Jupiters, I'm co-leading a project on that. So if you have any questions, please feel free to email me or come flag me down. Please also, if you're interested in any project, it really doesn't hurt to reach out to your prospective advisors to say, hey, would I be a good fit, or ask any questions about the project. So thanks.
Question. Yes.
I believe it is, yeah.
Yes, the executive director of NextEye says yes.
Yeah, there's a lot more information on the website, so be very careful to look at all the requirements for projects. Preferably, you'll be done with your classes by the start of
Any other questions? Yeah, and you can email Kevin, or I'm sure there's a contact on.
Yeah, Patrick Lord.
Oh yeah, right, Patrick. Yeah. Okay. Yeah. So just feel free to ask any questions, and you can come hang out with us at IPAC for 6 months. Okay. We made it.